Hey y'all, in the last lesson we dealt with finding area of circles and sectors. Remember, sectors are just like a part of the circle. Today we're going to apply some of that. We're going to be dealing with what we call geometric probability. But just as a reminder, and this isn't typed on your notes, but I wrote it at the top here to remind you of just in general, what does probability in math mean? Here it says the probability of an event happening is going to be equal to the number of ways that that event can happen divided by the total number of outcomes. It's kind of like if we said, what's the probability of you tossing a coin in the air and it landing on heads? Well, there's one way that that can happen because one of the sides is heads. So that would be the numerator, the number of ways for your event to happen. But the total number of things that could happen would be 2 because you could get heads or tails. And so your probability of it landing on heads would be a half. Or if you were to roll a die, which is the singular form of dice, and let's say you had one that had numbers 1 through 6 on it, what's the probability that you would land on a 2 or 5? Well, there's 2 ways you can do that. You can either land on a 2 or a 5. So that would be the number of ways that it could happen. But when you throw it, there's 6 possible ways. You could land on 1, 2, 3, 4, 5, or 6. And so our probability would be 2 over 6, which would reduce to 1/3. Today we're going to focus on taking probability and relating it to specifically geometry. So it says that it involves using principles of length and area, both of which we've been covering all year, to find the probability of an event. So we're going to start off with probability and length, and here it says the probability of getting some point, they're naming it K, but some point that lies on segment CD is going to be equal to knowing what the length of CD is, because any point on that length would be a point on CD. And then we're going to divide that, we're going to put it over the length of the entire segment AB. So let's take a look at example 1 and see how we can apply that. It says point K is chosen at random on segment DI. Find the probability that K is on the indicated segment. So for letter A, we want K to be somewhere on segment EF. So according to what we just learned, we know probability means how many ways can I get what I want over the total number of ways there are. Now look at EF, the length of EF. E is on 1, F is on 3. That gives us a length of 2. So we have a 2 for our numerator because our point could fall on any part of that segment EF. And then we want to put that over the total number, which is talking about the entire line segment of DI. So if D starts at 0 and I is at 10, that gives us a length of 10. So if it were to land, the probability of it landing on EF is 2 over 10, and we always want to reduce our fractions, and our final probability is 1/5. Now you can leave it as a fraction. If you want to change it to a percent, that would be 20%. So I'll leave that up to you. I'm personally going to leave mine as fractions unless otherwise asked. So we're going to do the same thing for letter B. We want to know what's the probability of a point randomly being chosen and being on segment FI. So first we need to know how long FI is. Well, it starts at 3, it ends at 10, so that is a distance of 7 units over the entire length of DI, which we already figured out for the last problem is 10, and that does not reduce, and so that's our final answer. So part C, we want to know the probability of randomly choosing a point and it being on GH. So looking at segment GH, it goes from 6 to 7. That's a length of 1 over, again, we're going to have 10 in the denominator because that's the length of the entire segment, and 1 over 10 does not reduce. All right, we're going to apply this now to area. So it says if a point in region A is chosen at random, notice region A is the entire shape, right? It's everything. Then the probability that the point is in region B, which is inside of region A, is going to be the area of region B over the area of region A. It is the same concept as what we just saw with the length. On those problems, we did the length of what we wanted over the length of the whole thing. Here we're going to do the area of the region that we want to land in over the area of region A, which is the whole thing. So again, this is part over whole. Think about what it means to be a fraction, part over whole. All right, so example number 2, find the probability that a point chosen at random in the square lies in the shaded region. Well, we look here, we don't actually have any numbers, do we? We don't know really a whole lot about the sides. What we do know is that these two segments are congruent. And so that means that this right here is the midpoint. Well, what if you were to draw a line straight down? What would happen? Well, a couple things would happen. First of all, we're creating a right angle. If I were to go straight down, if that were the distance, that's also going to land here at the midpoint over here, which is going to make these equal as well. We do know that this is a square, so it would make sense that these sides are congruent to this. So if you look at what we have, we want to land in the shaded region. Well, how many shaded regions are there? 1, 2. And they're equal, right? So there's 2 places we could land. Now, if we look at the picture as a whole, how many of those places of the same size exist? This, and this, and this triangle, and this triangle, all 4 of those are equal. So we want to land in the shaded region, which is 2 of them, but we have a total of 4 of the same equal size triangles to land in. So 2 over 4 would reduce to 1 over 2. Again, if you want to change that to 50%, you can. All right, number 3 says find the probability that a randomly chosen point in the figure lies in the shaded region. So again, we want to do the area of what we want. And what is it that we want? We want the shaded part. So the area of the shaded part over the total area where it can land. So that's the goal. That's how we're going to do probability. The area of what we want, which in this case we want to be in the shaded part, over the total area. So let's think off to the side. Let's just go over here and talk about a couple things. Let's start with the total area, because I find finding the total is usually a great and easy place to start. Total area is going to be the square. How do I know it's a square? Because the sides are the same value. How do you find the area of a square? Base times height, length times width, side times side. Pick one of those 3. Doesn't matter. I'm going to do side squared, side times side, and each side is 8. So the total area is 64. Hopefully that makes sense. So 64 units squared represents that I could land anywhere in here, anywhere in that square. So that gives us the denominator. All right, but now we need the numerator, which is to find the area of the shaded region. So here's where you have to put your thinking cap on a little bit. How do I find the blue area? Because that is an irregular shape. It's not something that I know a formula of to find those 4 blue sections. Well, here's what we can do. So if I want the shaded area, first, before I deal with numbers, I'm just going to deal with the whole concept. I would first need to find the area of the square because it's the big shape, right? Then I want to subtract the part that I don't want. The part that I don't want is the white part, which is what shape? It's a circle. So if I can find the area of the square and subtract from that the area of the circle, that's going to give us the part that we want, which is the shaded blue part. So let's start with the square because we've already found it. We know that it is 64. Now we need to find the area of the circle. So this brings back what we did yesterday, area of a circle, right? We need to do the formula pi r squared. So I'm just going to write a little note over here. We need pi r squared. Okay, well, let's go back and look at the picture, because in the picture I do not see a radius drawn. So let's go draw a radius. Remember, a radius is going to start at the center and it's going to go from the center to the edge. Now, I did not have one drawn in there, but here's what I want to show you. If I were to continue this line, and I'm just drawing a dotted line here, if I were to continue that, this whole thing from this edge to this edge represents what of the circle? It represents the diameter of the circle. What do you guys remember about a diameter? A diameter is twice as big as the radius. Here's another thing we know in this picture in particular is that all the way across that square is a measurement of 8. So if all the way across is 8, then that means that the radius has to be 4. So I'm going to do pi times r being 4 squared. That's how I'm going to find the area of the shaded region. So 4 squared turns into 16. So my shaded area is going to be 64 minus 16 pi. And that's what I'm going to put, well, first I have to write it correctly, but that's what I'm going to put in the numerator. 64 minus 16 pi. Now at this point, we're going to use a calculator. So let's get a calculator out. Now when you use a calculator, you have to be very careful about how you plug that in. All right, so hopefully you see my calculator. If you were to type it in just like it's written, so if I were to do 64, I don't know if well, it helps if you turn it on, Ms. Wingard. All right, 64 minus 16 pi, and then divided by 64. I can already tell you that this answer would be incorrect, and let me explain why. The calculator is going to do the order of operations. So according to the way that I've typed it in, division would come first. So the calculator would do 16 pi divided by 64. And then it would take that answer, whatever that answer is, and it would subtract it from 64. But what we really want is to have this entire value in the numerator being divided by 64. So you notice I put parentheses around it. That's going to be the difference between a right and a wrong answer. So I'm going to do parentheses 64 minus 16 pi. Then I'm going to close my parentheses and I'm going to divide that by 64. Now I will tell you, if you're using a calculator like this one, and there's the answer, but I'll come back to that in a minute. I have this calculator also in Math Print, so that button right there that has N over D, which stands for numerator over denominator, if I hit that, I get a fraction. If you use that button, there is no need to put parentheses around the numerator. So I would just type in 64 minus 16 pi, then I would use my arrow button to make my blinking cursor go down to the bottom, and that's where I would type in a 64. So if you decide to use the Math Print, which is wonderful, then you don't have to worry about putting parentheses in there. But just as a reminder, if you don't put this, if you have it just like I have it right here, and you don't put parentheses in there, you would get the wrong answer. So according to our answer, we get kind of an ugly number. For our sake, we're going to round it to the nearest hundredths place. That's 2 digits behind the decimal point. So the 4 is the third digit. It tells us to keep the 1 the same. So my probability for this is going to be approximately, again, I'm not going to use an equal sign because I'm rounding, 0.21. So a little bit over 20% would be the probability of a point randomly being in the blue shaded area. Okay, so let's take a look at example 4. It says find the probability that a randomly chosen point in the figure lies in the shaded region. So this is going to start off a lot like the last one did. I'm just going to write area of shaded region. I'm going to leave off the word region because I'm going to run out of room. Area of the shaded part over the total area. All right, so we need to find two things. I'm gonna start with the total area first. So first thing I have to do is recognize what the shape is of the total area. That's a trapezoid. Do you guys remember how to find the area of a trapezoid? I'm gonna put a little T down there for trapezoid. This is where we learned that song. Trap, trap, trapezoid, base 1 plus base 2, multiply by the height, then divide by 2. Or you could maybe remember the formula. Whichever works in your head. It doesn't matter to me. All right, so I got 1/2. Now I need to know the height of the trapezoid. Remember, the height has to form a right angle with the bases. So according to this picture, the height is going to be 12. All right, then I need to add the bases together, and according to the picture, the top one is 10 and the bottom one is 16. All right, so 1/2 of 12 is 6, and then in parentheses, 10 plus 16 is 26, and then I'm gonna multiply those two numbers together, and 6 times 26, I believe, is 156. So we currently know the denominator, the total area. All right, now we want to find the area of the shaded part. So this problem is a little bit different from the last one. In the last one, we had an irregular shape. So the way we did it was we did the big shape minus the inside shape that we didn't want. So we did square minus circle. But in this picture, the shaded area is a shape that we know. What is it? It's a rectangle, right? This yellow shape is a rectangle. So how do we find the area of a rectangle? Base times height, length times width, either one of those will do. So what would be the base and the height? The base is going to be 10. The height is going to be 12. And so that means that the area of the shaded region is 120, which is going to be our numerator. All right, so we have the shaded region over the total region, and then let's see, I know both of those are divisible by 4. Let me try that. So 120 divided by 4 is 30, and 156 divided by 4 is 39, and those numbers are both divisible by 3. 30 divided by 3 is 10. 39 divided by 3 is 10 over 13. Now, if you wanted, because we were using a calculator for the last problem, we could have done 120 divided by 156. That should be the same thing as what 10 over 13 is. Yep. So if you want to leave it a fraction, you can, or if you want to rewrite that in the form of a decimal, I would say that that is approximately 0.77. All right, example 5, find the probability that a point chosen at random in the circle will be in the given section. So we're going to start off with, we want it in A. So we want to know, it's like what we had before, where in the numerator you're going to put how many ways can you get what you want. The denominator is going to be the total number of ways. This is a little bit different because it's a circle and we have angle measurements. So for A, what's the angle measurement? 50 degrees. What do you know about the measurement of an entire circle? 360. So that's pretty easy, right? And then both of those numbers are divisible by 10, and we get 5 over 36. And some of you might rather have it as a decimal, so 5 over 36 is going to turn to approximately 0.14. So I think C and D will be easy to do as well. So if we land in section C, that is 60 degrees over a total of 360 degrees. That reduces to 1/6. If I am not mistaken, that's going to turn into 0.17, but let's try it with the calculator because sometimes I screw up. I got it. All right, and then landing in section D. Section D is a 40-degree section out of an entire 360-degree section. Both of those numbers are divisible by 40, so I'm going to get 1/9. I believe that's going to be 0.11, but let me check it just in case. 1 divided by 9, yep, 0.11. Okay, last problem. Says Joanna designed a new dart game. A dart in section A earns 10 points, a dart in section B earns 5 points, and a dart in section C earns 2 points. Find the probability of earning each score. Okay, we're just gonna do two. We're gonna do probability of earning A, and we're gonna do probability of earning the score in C. Let's just do those two. I think if we do two, that's good enough. Okay, so we're gonna start it off the same way. We want area of A, because that's what we want, over the total area. Does that make sense? So we want to land in part A. We want to land in section A, so we need the area of section A over the total area. So here we go. Let's talk about area of A. All right, well, that's a circle. So that's pi r squared. Now, according to our information over here, circle A has a radius of 2. So I'm going to plug in a 2, and I'm going to get 4 pi. So my numerator is 4 pi. All right, now let's do total area. Now, total area is everything in the big circle. That's going to cover all of it. It's going to cover the one in the middle, well, I should say this one right here. Then it's going to cover what's going on in B, and then it's going to cover what's going on in C. So that means the entire circle. That's what that means. Again, we're going to do pi r squared. So, looking at the picture, we need to know the radius of the big circle, which they tell us right here, 10. So that is going to equal what? 100 pi. So that is the denominator. So we have 4 pi over 100 pi. Well, both of them have a pi, so I can divide that out. That leaves me with 4 over 100, which I can reduce both of those numbers by 4. So that turns into 1 over 25. You are welcome to leave it like that. That would also change into 0.04 if you would prefer a decimal. So the probability of us being able to land in A and be able to earn those 2 points, and maybe that's what I should have called it instead of probability of A, probability of getting 2 points, because I needed to land in A over the total area. That's probably a better way to call it. So let me rename this one while I'm at it. Let's find the probability of earning. What do you get for, no, that was, oh man. I really got to do these videos earlier. Okay, sorry. If we landed in A, we would have gotten 10 points. So much better. Okay, now let's do what happens if we were to land in section C, thus getting 2 points. Let's try that out. Okay, so we need to find the area of section C, and we're going to put that over the total area. So we want to land in C. That's how we can get it right, but we have to put it over the total area. Good news is we already know the total area because the total is not going to change. So the total area is 100 pi. But we need to do some work down here because we need to find the area of section C. So if I want this that I'm shading in, if I want to land in C, what do you guys think I would need to do? Well, it's kind of like we saw in example 3. We wanted the blue area, so we had to do the big shape and then subtract out this inside shape to get those weird irregular shapes. It's kind of the same thing here. We need the big circle. Then we're going to subtract out not the smallest circle, but the medium sized circle. So big circle minus medium circle. I hope that makes sense. Now the big circle is otherwise known as the total area, which we already know is 100 pi. But now we have to find the medium circle. So we're going back to our formula of pi r squared. And that is, the medium circle is going to use this as a radius from the center to the edge of B, which right here they tell us is 5. So we have 100 pi minus 25 pi, which simplifies to 75 pi, which is now our numerator. So we have 75 pi over 100 pi. They both have pi. It's going to divide out. We're left with 75 over 100. 75 over 100 reduces to 3/4, which is also known as 0.75. So if you were trying to earn 2 points, you have a 75% chance of getting it. If you were trying to earn 10 points, you only have a 4% chance of getting it. It would be much harder for you to get it right in the middle. Okay, hopefully you feel pretty good about that lesson. Your homework assignment is the geometric probability worksheet that you got in the packets that y'all picked up on Monday. Now, if you look at it, you will notice that it goes 1, 2, 3, 4, 5, 6, and then you turn it over and it goes to 14, 15, and 16. I left the whole page out. I was just trying to make it a little bit easier for us. So, that being said, you do not have to do number 6 on the front, so you have to do 1, 2, 3, 4, 5, and then do all of the problems on the back, okay? I'll try to remember to put that in RenWeb, but if you listened to the video, then maybe you've one-upped everybody else. And I will see you guys in our next Zoom session, which I think is happening tomorrow, so I'll see you guys then.